Hi, good day. This is Apinado, and today I will be discussing slotted waveguide antenna. So, slotted antenna arrays used with waveguides are popular popular antenna when it comes to navigation, radar, and other high frequency systems. They are simple to fabricate. They have low cost, especially high antenna efficiency. They radiate linear polarization with low cost polarization. So, these antennas are often used in aircraft applications because they can be made to conform to the surface on which they are mounted. The slots are typically thin, less than zero point 0.1 of a wavelength, and zero point 0.5 wavelengths long at the center, the frequency of operation. The slots on the waveguide are assumed to have a narrow width. Increasing the width increases the bandwidth. Recall that a fatter antenna often has an increased bandwidth. With the expense of a larger width is a higher degree of cross polarization. The fractional bandwidth for thin slots can be as low as 3 to 5%. Wide slots can have a FBW on the order of 75%. An example of a slotted waveguide is this. So this is called, the figure one is basic geometry of a slotted waveguide antenna. As you can see, in the cavity, the back slot antenna, each slot could be independently fed with a voltage source across the slot. However, especially for large arrays, this would be very difficult to construct. Instead, the waveguide is used as the transmission line to feed the elements. So, the position, the shape, and the orientation of the slots will determine how far or and if they radiate. In addition, the shape of the waveguide and the frequency of operation will play a major role. To understand what is going on, we will need to understand the fields within the waveguide first. So here the dominant TE10 mode will be assumed to exist within the waveguide. So using the figure 1, the the basic geometry, the fields that exist within the waveguide are given by this equation. So F So above, F is the frequency of interest, K is the wave number, and of course E sub O is a constant that specifies how much power is added to the waveguide. So for question number 1, we will need to give the label of this. So yeah. So the magnetic field tangent to a conductor produces electric currents on the surface. That results to the surface current density, J, measured in amps per meter, can be determined using the unit normal to the surface N as this. J is equals N hat X, times H. On the top wall of the waveguide, where the slots are, the induced currents will be like this. So from this to this. We all know that radiation occurs when the current must go around the slots in order to continue in their desired direction. As a sample, as an example, consider a narrow slot in the center of the waveguide as shown in figure 2. A waveguide with a thin slot centered is width. So, figure 2. A waveguide with a thin slot center about its width. In this case, the Z component, where the Z component of the current will not be disturbed because the slot is thin and the Z current would not need to travel around the slot. So the X component of the current will be responsible for the radiation. However, at this location, we can see X is equals to A over 2. The X component of the current density is 0. So no current, and therefore there will be no radiation. As a result, slots cannot be placed in the center of the waveguide, as shown in this figure. So if the slots are displaced from the center line, as shown in the figure one, wait, where's the figure one? Like this, the X directed current will not be 0 and will need to travel around the slots, so there will be radiation. So note that the distance from the edge will determine the magnitude of the current. As a result, the power that the slot radiates can be altered by moving the slots closer or farther from the edge. So in this manner, a phased array can be designed with varying to each element. So this is figure 3. So if the slot is oriented just like this, the slot will disturb the Z component. The Z component of the current density. This slot will then radiate, so there will be radiation. If this slot is placed away from the center line, the amount of power that it radiates can be adjusted, so you can adjust the radiation. So the horizontal slot in the waveguide, if the slot is rotated at an angle about the center line, as shown in figure 4, it will radiate. Okay, so we will have another question. So which of these figure has no radiation or will not allow radiation to pass through? So it is this. Am I right? Yeah. So figure 4. We go in figure 4. So the power wait so the power it radiates will be a function of the angle phi that is rotated, specifically given by this equation. Sine raised to 2 phi. Note that the Z component of the current is still responsible for radiation in this case. The component is disturbed, however, the currents will have opposite magnitudes on either side of the center line.